Have you ever wondered what lies beyond our solar system and the vast reaches of the universe? This is a question that has ignited the imaginations of countless generations of scientists, explorers, and dreamers. Beyond the planets of our own neighborhood, and even beyond the glittering sea of stars that make up our Milky Way, there exist vast and unknown territories that sit almost at the very edge of what we can conceive. To understand what truly resides out there, we must embark on a long narrative journey. We begin today with the Mebius segment, but before we dive in, please remember to like and share this program. Located approximately 450 light-years away, the protoplanetary disk of H L Tauri presents details that span across both time and space, offering insights far beyond its physical scale. This young star, which is no more than 1 million years old, possesses a disk of startling complexity that appears far more mature than anyone had predicted. Observations reveal a series of concentric rings and sharp gaps, strongly suggesting that newborn planets are using their gravitational influence to clear paths through dense material. Although these planets remain invisible to our direct gaze, their presence is felt through their gravitational signatures, and their formation may be occurring much faster than our linear models previously suggested. These clear structures are forcing the scientific community to re-evaluate the timeline of planet formation and are challenging long-held assumptions. Within the disk of H L Tauri, dust does not settle in a uniform fashion. Larger particles tend to drift closer to the star while finer grains remain widely dispersed. This distribution pattern hints at dynamic forces actively sculpting the system. The unusually high dust-to-gas ratio suggests that the chemical processes occurring here differ significantly from more evolved systems. These ratios not only govern the evolution of the disk but may also dictate the types of planets that will eventually emerge, influencing their core compositions and eventual atmospheres. Snow lines within the disk mark regions of distinct chemical activity. These frozen zones play a critical role by allowing volatiles to accumulate and solidify, providing the necessary raw materials for the cores and atmospheres of future worlds. Closer inspection also reveals anomalies in the distribution of matter, where some gaps are wider than expected, hinting at gravitational instabilities that could cause the disk itself to fragment. Such instabilities might give rise to gas giant planets through a process very different from the traditional slow buildup of rocky cores. Gas flowing through these gaps toward the planets resembles a process where young worlds graze on material like sheep in a field. This movement is not random but is shaped by the complex interplay of gravity and radiation. Simultaneously, the disk appears to be losing mass through a faint disk wind, which further rewrites its structure and limits the total amount of material available for planetary construction. The behavior of the H L Tauri disk echoes processes found in much more distant parts of the cosmos, such as the cold spot in the cosmic microwave background. Both involve invisible forces manipulating structures behind the scenes. The cosmic microwave background cold spot is a region that is relatively cooler than its surroundings, possibly corresponding to a supervoid or even a glimpse of something beyond the observable universe. Similarly, the environment surrounding H L Tauri is shaped by forces that are not immediately visible but leave a clear mark on the disk. These patterns remind us that unseen processes often dominate the evolution of cosmic systems. Like H L Tauri, brown dwarfs occupy a blurry middle ground between stars and planets. Commonly found in nearby extragalactic systems, they challenge our understanding of stellar formation. They lack sufficient mass to sustain continuous nuclear fusion, yet they form in a manner more akin to stars than planets. Studies of brown dwarfs in neighboring galaxies reveal that even tiny variations in mass and environment can lead to vastly different celestial outcomes. These dimly lit dwarfs act as cosmic laboratories, providing clues about the conditions that might influence disks like H L Tauri. When a massive celestial object passes between Earth and a distant star, its gravity bends the light of the background star, temporarily magnifying its brightness. These gravitational microlensing events have already revealed the existence of planets, black holes, and even rogue stars wandering through interstellar space. If this technology is applied to systems similar to H L Tauri, we may be able to detect planets that are too dim or too small to be seen directly, providing a complementary tool for the study of distant protoplanetary disks. Instruments capable of detecting Cepheid variables allow us to extend our reach even further. Cepheid variables are famous for their predictable, periodic pulsations in brightness. Because there is a strict relationship between their intrinsic luminosity and their pulsation period, they serve as standard candles for measuring cosmic distances. Just as the disk of H L Tauri provides a progress map for the stages of planet formation, Cepheid variables provide a ruler for mapping the universe on a grand scale. Through this staged and comparable method, scientists can calibrate evolution models for planets and planetary systems. The reason Cepheids work as cosmic rulers is due to the pulsation mechanism in their outer layers. They brighten as they heat and expand, and dim as they cool and contract. The period luminosity relationship gives us their true brightness, which, when compared to their observed brightness, reveals their distance. Cepheids are widely distributed from dwarf galaxies to the disk of the Milky Way and beyond. In infrared observations, they can pierce through thick cosmic dust, revealing regions that were once hidden. This dust-piercing ruler is essential for mapping the spiral arms of the Milky Way and characterizing the structure of the galactic disk. Their application in starburst galaxies is particularly critical, providing stable anchor points amid the dazzling and complex noise of star formation to calibrate distances and constrain the physics of stellar environments. On the cosmic distance ladder, they work in tandem with dwarf supernovae to extend our measuring range to hundreds of millions or even billions of light years. Recent discrepancies regarding the expansion rate of the universe stem from the tension between Cepheid-based paths and other methods. This requires us to make more refined corrections for second-order effects like metallicities and the influence of binary companions. Cepheids also participate in the characterization of galactic dynamics. By combining position and velocity, we can map structures and capture movements to test the effects of gravity in different environments. Their presence in unusual galaxies proves the universality of this method, and discoveries in ultra-low surface brightness dwarf galaxies have expanded our understanding of the edges of the cosmic web. With the release of high-precision data from the Gaia mission, our calibration of the intrinsic properties of Cepheids has become even more rigorous, making every step of the cosmic distance ladder more secure. High-latitude molecular clouds in the Milky Way act as reservoirs for organic matter and cold gas. Much like the material surrounding H L Tauri, these clouds are hotbeds of chemical activity. Observations of such regions allow us to glimpse the formation of early disks. Molecules condense under the shadow of gravity, paving the way for the birth of stars and planets. The presence of organic compounds also suggests the possibility of prebiotic chemistry, tracing the origins of life back to the earliest stages of planetary development. These isolated, cold clouds are like quiet retreats away from the noise of the galactic center. Temperatures near absolute zero allow for the birth of molecules that could not survive in warmer regions. The detection of organic molecules like methanol and formaldehyde suggests that complex chemistry can occur even in these sparse places. Many of these clouds lack the bright fires of active star formation and may represent an even earlier stage of evolution or have remained quiet for millions of years. This does not mean they lack potential, a mere nudge from an external shock wave or gravity could ignite the cold and transform it into a cradle for new stars. In the vicinity of the Milky Way, the giant star regions of satellite galaxies and the local void share a strange dynamic that mirrors the unexpected forces in the H L Tauri disk. Both require new explanations to account for their behavior. The lack of gravitational pull in the local void affects the motion of galaxies, while the environment of H L Tauri suggests that the underlying interactions cannot be described by simple gravitational models alone. The impact of the local void on the velocity differences of surrounding galaxies is seen in subtle deviations in the Hubble flow, where recession velocities in certain directions are slightly lower than average, suggesting that gravity in this region is shallower. Data on galaxy distance and velocity in this area show systematic variances that require second-order corrections to Tully-Fisher relations and distance calibrations. High-resolution density field re-examinations show shear zones near the boundaries of the void, where galaxy trajectories bend to form anisotropic streamlines. Extending this effect to larger scales might explain some velocity anomalies in the local group, the Virgo supercluster, and the Laniakea superstructure, linking a matter-deficient region to the broader cosmic velocity field. The gamma-ray halos around active galactic nuclei represent another similar point of reference, where high-energy particles escape extreme environments and diffuse into vast intergalactic space. Studying these halos helps us understand how energy transfer and particle acceleration happen on a large scale. Similarly, the nearly invisible disk winds of H L Tauri reveal how energy and matter flow within young stellar systems, shaping their evolution in subtle yet profound ways. Unlike the active stage of H L Tauri, isolated neutron stars are often found drifting alone through interstellar space. Studying these remnants, which barely interact with their environment, brings us back to the fundamental mechanisms of stellar evolution. In contrast, the defining characteristic of H L Tauri is its continuous dynamic interaction with its disk. The outflow of material from H L Tauri even shares a certain structural similarity in scale with the Fermi bubbles, the giant gas outflows at the center of the Milky Way. Whether in a newborn star or a galactic center, massive energy releases drive the movement of gas, rewriting the cosmic environment and affecting regions far from the source. Structures across extreme scales are presenting this shared reality. Ultra-faint dwarf galaxies orbiting the Milky Way mirror the precise sculpting seen in H L Tauri. The delicate mechanical balance required to form these extremely dim small galaxies shares commonalities with the finely tuned ring systems of H L Tauri. These formations may be relics of ancient cosmic interactions, preserving details of early history. Though H L Tauri is young, it preserves a snapshot of the stages of planetary birth, freezing the image of what our own solar system might have looked like billions of years ago. Ultra-faint globular clusters found in the outer reaches of the Milky Way provide another layer of connection. The formation of H L Tauri is like a time capsule, presenting the initial state of the solar system frozen in its youth. Neutral hydrogen bridges between galaxies act as interstellar channels for material transport, just as gas flows between stars and dust and gas flow within a disk to feed young stars and shape planetary systems. In contrast to the new worlds being assembled in H L Tauri, some photons in the universe wander alone, having been ejected from their original systems by dynamic interactions. This shows how planetary systems can be built or destroyed in violent processes, while H L Tauri represents a system being built rather than torn apart. High-energy photons ejected from active galactic nuclei collide with background photons in the intergalactic medium, producing electron-positron pairs that bend in intergalactic magnetic fields, forming nearly isotropic diffuse gamma-ray halos. The brightness profile of these halos, coupled with magnetic field strength and historical activity, acts as an archaeological record of cosmic magnetic fields. A steep edge to the halo implies intermittent energy injection, while a smooth profile supports continuous acceleration with a low duty cycle. Analyzing these samples helps set lower limits for intergalactic magnetic fields, influencing our understanding of the thermal history of large-scale structures. Isolated neutron stars that are not attached to supernova remnants often appear as X-ray sources or radio pulsars. Their spin-down indices deviate from ideal magnetic dipole radiation values, suggesting that magnetic field geometry, plasma winds, or internal superfluid coupling are at work. Although they are below the threshold of a supernova, they show signs of fallback disks, indicating that small amounts of material left over after a supernova still interact with the stellar magnetosphere, causing rotation noise and occasional pulsar glitches. The statistical properties of isolated samples help predict the equation of state for dense nuclear matter, linking radius and mass intervals to nuclear symmetry energy parameters. The double bubble structure at the galactic center, with its closed boundaries and rigid shape, may have been caused by short-lived activity in the galactic core tens of millions of years ago. Multi-wavelength consistency supports a multi-stage injection scenario, where an initial burst pushed up hot gas and cosmic rays, followed by a weaker injection to maintain a brightness plateau. The bow shock edges outside the bubbles and the internal turbulence scales provide a local specimen for understanding the coupling between galactic nuclei and their disks. These small, low-surface brightness galaxies, dominated by dark matter, are considered fossils from the era of rionization. Their stellar populations have extremely low metallicity and enhanced alpha elements, recording a brief, one-time star formation event in the early universe. Tidal disturbances are particularly noticeable in them. Long tidal tails and debris streams near the galactic center, modeled through chemical tagging and dynamics, can reflect original mass and orbital history, thereby tracing the small-scale structure of the galactic dark halo and the free-streaming scale of cold dark matter. Globular clusters located at the edges of galaxies often share space with tidal streams. They lack dark matter envelopes and have small internal velocity dispersions. The Milky Way acts as a sensitive platform for the behavior of Newtonian gravity in weak fields. Stellar archaeology shows that their upper age limits can reach 120 to 130 billion years, serving as one of the time benchmarks for the early assembly of the galaxy. Neutral hydrogen bridges formed by tidal forces or ram pressure stripping span the intergalactic space between neighboring galaxies, acting as channels for matter redistribution. The low-velocity shear turbulence and metallicity gradients on these bridges help date the time and geometry of close encounter events. Some clusters on these bridges will trigger massive star formation once they cross a density threshold, giving birth to tidal dwarf galaxies. Thus, these bridges are both footprints of interactions and reservoirs for future stars. If certain segments of the cosmic web become decoupled from the main filaments due to early fluctuations or late-stage nonlinear evolution, low-coupling cosmic islands appear. These manifest as absorption zones that are out of sync with the surrounding Hubble flow. On the other hand, multi-body scattering and tidal interactions in planetary systems can eject planets in groups, forming temporarily related clusters of rogue planets. These can be detected through microlensing surveys and deep-field infrared coordination. If spatial correlation exists, it will support the scenario of group ejection rather than a simple random distribution. Voltage drops driven by magnetospheric plasma drive pair production and the formation of radiation cones. Observed subpulse drifting and polarization angle swings are products of the geometry between the magnetic axis, rotation axis, and the line of sight. Pulsar wind nebulae are visible around some isolated stars, where bow shock profiles provide transverse spatial velocities that intersect with velocity models from parent supernovae. Long-term timing can also measure the evolution of the braking index, reflecting the internal physics of magnetic field reconfiguration and superfluid vortex unpinning. While plasma life remains speculative, nonlinear self-organized structures like vortices and solitons in high-energy plasma environments can maintain ordered states far from equilibrium under specific external drives. Laboratory plasmas show the beginnings of shape retention and information encoding, but there is no direct evidence of life in astronomical environments. The significance of this research lies in exploring whether computable, feedback-driven self-organizing systems can emerge on non-organic platforms, thus expanding the possibilities for life. The long, ribbon-like stellar streams surrounding the Milky Way are fossils of early mergers. They are stretched along their orbits and sheared by the galactic gravitational field. Through their three-dimensional geometry and velocity distribution, we can reconstruct past disturbances and detect the signatures of dark matter subhalos. If sharp gaps or ripples are found in these streams, they are likely caused by the passage of dark matter subhalos with masses between 1 million and 100 million times that of the Sun, providing key evidence for the small-scale problems of cold dark matter. Hypervelocity stars are mostly explained as binary components that escaped after the tidal disruption of a twin by an invisible supermassive black hole. Others originate from three-body scattering in dense clusters. They escape the galactic disk at hundreds or even thousands of kilometers per second, becoming probe particles for the outer edges of the galactic gravitational field. If groups of high-velocity stellar streams are confirmed, it implies a common dynamical starting point, and their spatial angles and velocity tensors can backward constrain temporal geometry. High-energy astrophysical neutrinos serve as unbiased probes, particularly as they pierce through dust and magnetic fields to point directly to the source of acceleration. Neutrino events observed by telescopes are correlated in time and direction with blazar flares, starburst galaxies, or tidal disruption events. As detector arrays expand, single correlations will move toward population-based evidence. Simultaneously, these parameters provide independent constraints for particle physics. This is the intersection of astrophysics and particle physics. The detection of neutrinos, which are nearly massless and travel at near the speed of light, has become one of the most fascinating tools for exploring the universe. Although they are extremely difficult to catch, the data they carry is enough to change our understanding of things and processes still hidden by traditional observation methods. When a gamma-ray burst occurs, a massive amount of energy is released in a single moment. These bursts are not only dazzling in the gamma-ray spectrum but also produce high-energy neutrinos. Unlike gamma rays, neutrinos are almost never scattered or absorbed, allowing them to directly record the energetic processes driving these explosions. Neutrinos from these bursts provide clues to the energy levels required to drive such cosmic spectacles, giving us a glimpse into the birth and death of some of the most massive stars. Spinning neutron stars also produce neutrinos during their violent interactions. When these deadly remnants born from supernovae collide with each other, the event releases a surge of neutrinos along with gravitational waves. These neutrinos reveal the physical conditions for the synthesis of heavy elements like gold and platinum. Observations of such collisions provide a new perspective on the behavior of matter under extreme density and pressure that cannot be replicated in laboratories on Earth. Deep in the ocean, neutrino detectors like those in the Mediterranean use seawater to track the faint signals of these particles. Unlike traditional observatories, these underwater experiments use the natural clarity and depth of the sea to detect neutrino interactions. This unique environment allows researchers to identify neutrinos from distant celestial sources and reveal the paths of particle propagation across cosmic scales. Neutrinos produced by pulsar wind nebulae are another important data source. As the rotating remnants of massive stars, pulsars collide with the surrounding medium using charged particle winds moving at near the speed of light, generating neutrinos. By analyzing these neutrinos, scientists can gain insight into how pulsars transfer energy to their surroundings, creating nebulae that glow with high-energy radiation. Solar flares, which are massive eruptions on the surface of the Sun, also generate neutrinos. These events occur when the Sun's magnetic field suddenly reconnects and accelerates particles to high energies. Neutrinos produced during flares provide clues about solar magnetic activity and the mechanisms driving these high-energy eruptions. Such observations not only deepen our understanding of the Sun but also reveal how particle acceleration works within the solar system. When a star gets too close to a supermassive black hole and is torn apart by tidal forces, it results in a tidal disruption event. These violent interactions release neutrinos that can travel through chaotic disorder over long distances to reach Earth. Observing neutrinos from these events helps us understand the extreme environment around black holes and reveals processes that are difficult to see directly in traditional electromagnetic bands. Earth itself is now a massive lens for sparse neutrino layers. Researchers examine the attenuation and spectral modulation of neutrinos as they pass through Earth to map its internal structure. This provides a non-invasive way to study the material and state of the mantle and core, allowing us to peer into the deep Earth without drilling. The interaction between neutrinos and polar ice is another frontier of innovative research. Stations at the South Pole use the high transparency of ice to detect the faint flashes triggered by neutrino interactions. These signals connect us directly to distant cosmic events and preserve information from the early universe. In volcanic regions, neutrino detection experiments study the interaction between these particles and magma. Differences in how neutrinos interact with magma composition and density as they pass through volcanic material can be read, providing data on volcanic activity and magma movement. Regions with high supernova activity present unique neutrino radiation patterns. These supernova factories are natural laboratories for studying the final stages of massive star explosions. Neutrino observations from these regions deepen our understanding of how supernovae inject heavy elements into galaxies. Tracks left by neutrinos in ice sheets record their journey across the universe. These marks, spanning thousands of years, provide direct evidence for cosmic processes and act as time capsules of the ancient astrophysical world. When stars merge, they release neutrinos that capture the energy and processes of that violent event. These emissions reveal the physics behind stellar mergers and echo cosmic phenomena like gravitational waves. Seasonal fluctuations in neutrino detection rates reveal periodic changes in Earth's position relative to neutrino sources. These patterns provide information about the distribution of neutrino sources in the universe. Under extreme conditions, such as dense stellar environments, neutrino interactions reach the boundaries of theory and experiment. Experiments conducted in these scenarios study the behavior of neutrinos at high pressures and temperatures unreachable in laboratories. Spatial patterns of neutrino tracks recorded in the ocean point toward their cosmic origins. These patterns help researchers identify neutrino sources and reconstruct their paths across the universe. By passing through the interiors of planets, neutrinos can also indirectly image planetary composition, a method that may be used to study the internal structures of planets inside and outside the solar system. Neutrinos from stars in the universe provide real-time data for the stages of stellar collapse. These particles are directly linked to the process of energy release in death events like supernovae. Galaxy collisions produce neutrino radiation that reflects the energetics of the merger. These signals provide data on how galaxies evolve and transfer energy during a merger. Rapid neutrino bursts associated with space weather also track the movement of ice sheets while detecting neutrinos. This 2-for-1 data provides a dual perspective on cosmic events and Earth's environmental changes. High-energy neutrinos detected in star clusters reveal information about the interaction between stars and interstellar matter. These radiations show the distribution of energy and particles in dense stellar environments. The synthesis of elements inside stars leaves marks on the neutrinos they emit. By studying these particles, scientists can gain a deeper understanding of how stars contribute to the elemental abundance of the universe. Neutrinos can travel through dense galactic regions, making them ideal probes for mapping invisible matter between galaxies. These particles can map the distribution of matter and energy in the universe, revealing structures invisible to traditional telescopes. Some high-energy cosmic events that emit unexplainable neutrino bursts challenge existing astrophysical models. These rare detections point to unknown phenomena and push the boundaries of our knowledge. Energy transfer facilitated by neutrinos across vast cosmic distances connects scattered cosmic regions. By studying such transfers, scientists can track links between seemingly isolated astrophysical phenomena. Some compact binary systems, whose components orbit each other closely, emit neutrinos through their interactions. These radiations reveal the dynamics and evolutionary mechanisms of binary systems. Neutrino signals from billions of years ago are time capsules of ancient cosmic events. These almost undisturbed particles, traveling through space, preserve records of the earliest eras of the universe, connecting us to its origins. The universe is an endless mysterious canvas painted with phenomena that challenge our perception of reality. When the astronomical gaze looks beyond the familiar, exploring stellar streams at the edge of the galaxy and ancient fossil star systems hidden in galactic halos, we begin to glimpse the vast and intricate interconnection of the cosmos. All these discoveries remind us that those things located beyond the solar system, and even beyond the universe, are not unreachable shores but a narrative unfolding in real time, shaping the texture and beauty of existence. These hypothetical cosmic islands might preserve ancient relics untouched by expansion, offering various perspectives on the history of the universe. Much like the frozen frames of early planetary formation captured in the H L Tauri system, both serve as fragments of a much larger puzzle. The steady radiation of an isolated pulsar acts as a cosmic beacon, mirroring the hidden planets suggested by the gaps within the H L Tauri disk. Detailed mapping of this disk, combined with high-precision observations of pulsars, allows us to glimpse the dynamics, interactions, and invisible influences shaping their surroundings. As the system evolves, it remains a vivid example of how stars and planets are born. Even in its youth, a single system can reveal connections that echo across the entire cosmos. Its rings and gaps are more than structures, they are windows into the processes that shaped its destiny and perhaps the fate of the wider universe. Beyond the disk, on a cosmic scale, there are equally baffling mysteries. The cold spot in the cosmic microwave background is a classic example of such an anomaly. It stands out abruptly from the otherwise uniform afterglow of the Big Bang, appearing as a region significantly cooler than its surroundings. Due to its massive scale and notable temperature variance, located nearly 2 billion light-years away, this cold spot complicates our theories of the early universe. It is tens of microkelvins colder than the average temperature, a difference that seems small but demands a formal explanation. One hypothesis suggests it might be a supervoid, an incredibly empty region of space that weakens the gravitational lensing effect on photons passing through it. As these photons traverse the void, they lose energy and appear colder. However, even a void of this magnitude cannot fully account for the temperature gap. This discrepancy between theory and observation breeds further speculation. Many hypotheses look back to the inflationary period of the early universe, where inflation might have amplified quantum fluctuations, leaving behind density fingerprints. The cold spot could be a frozen relic of a density fluctuation, yet models still show it as a highly anomalous case that is difficult to explain by chance alone. This hints at potential processes beyond the standard cosmological model. Some place their bets on the multiverse. If universes can interact, a collision with another universe during our formation could have imprinted energy onto the background radiation, leaving behind an alienated cold spot. While speculative, this idea is not without foundation and, if proven, would redefine our understanding of cosmic boundaries beyond a single universe. Closer inspection reveals an intriguing feature: the internal statistical properties of the cold spot are non-Gaussian, deviating from the random fluctuations seen elsewhere. This non-Gaussianity complicates the issue, making it seem more like the product of an isolated world rather than a global process. Other studies link the cold spot to regional variations in dark energy density. If dark energy is not uniformly distributed, certain regions could exert a unique influence on space-time, altering the behavior of photons passing through. This ties the cold spot to one of the greatest unsolved mysteries: dark energy. Another fascinating idea involves cosmic strings. If the early universe left defects in the fabric of space-time, strings near the cold spot could cause distortions, creating temperature variations. Although not yet directly detected, their theoretical properties align with several features of the cold spot. We can largely rule out local contamination from our own galaxy, as research shows that galactic dust cannot explain this anomaly. This reinforces the belief in its cosmological origin, leaving little room for mundane explanations. However, its distance still brings uncertainty, as galaxy surveys in that region rely on premises that are not yet universally confirmed. The cold spot also aligns with certain cosmic alignments, raising questions about deep connections between it and local structures, potentially blurring the lines between the near and far reaches of the universe. Some suggest it is not a void but an overdense region where energy transfer was suppressed during the era of ionization. In this view, early cosmic structures interacted with photons in ways that created void-like features, providing insight into how galaxies and clusters were ignited within the chaos. The boundaries of the cold spot are also a mystery. Unlike the smooth transitions elsewhere, its edges are remarkably sharp. Such abrupt changes might be caused by constrained structural events, challenging our understanding of matter and energy distribution on the largest scales. Origin theories are also intertwined with the physics of inflation. If inflationary energy was not uniform, temperature variations might hint at multiple inflation fields working simultaneously. Other research guesses the cold spot could be a remnant of primordial magnetic fields, which would suppress matter distribution. Even more imaginative candidates include exotic particles like axions, where photons passing through specific regions have their energy altered through time-varying interactions. Some even propose it as a sign of quantum vacuum energy leakage, revealing an unknown level of quantum dynamics. Surveys of galaxies near the spot show sparse patterns, supporting the supervoid hypothesis, though the size and impact do not quite match, leading some to wonder if multiple smaller voids align to create the signal. The motion of nearby galaxies also seems pulled by the cold spot, showing specific velocity preferences. Numerical simulations show such a cold spot is extremely rare, pointing toward new physics or unknown phenomena. Photons crossing the area carry subtle clues about its nature, and their polarization patterns might eventually reveal interactions with invisible fields. Some scientists view the cold spot as a frozen piece of the primordial vacuum, unchanged since shortly after the Big Bang. Its gravitational potential might also cause time delays for crossing photons, providing another path to understanding its structure. Nearby, if giant satellite clusters exist and their distribution matches the cold spot, we might link this anomaly to the energy processes of early satellites. While the cold spot leads us to questions of cosmic balance, transition-type brown dwarfs in neighboring galaxies provide another piece of the puzzle. They bridge the boundary between stars and planets, lacking the mass to sustain hydrogen fusion but larger than typical planets. Existing in environments different from the Milky Way, these objects allow us to examine how substellar bodies evolve under lower metal abundance and different pressures. In nearby galaxies like the Magellanic Clouds, some brown dwarfs show atmospheric features distinct from their counterparts in our galaxy, with lower temperatures and unique chemical compositions. Despite low metal content, these dwarfs still form, challenging the intuition that high metallicity is a requirement. Even more extreme are free-floating brown dwarfs wandering through interstellar space without a host star, suggesting they can form spontaneously. Evidence for their origin is contradictory. Some research points to fragmentation during turbulent collapse, while others suggest they form directly in low-density regions. In some active star-forming regions of dwarf galaxies, brown dwarfs cluster near new stars, perhaps reflecting unique gravitational distributions. Their magnetic fields are particularly surprising, with strengths higher than expected for their mass, potentially driving exotic methane storms. In external galaxies, many rotate faster than those in the Milky Way, raising questions about how angular momentum is preserved. It is also possible that brown dwarfs possess their own planetary systems, where planets nurtured by their accretion disks might not be rare. Their spectral lines differ from those in the Milky Way, acting as chemical fingerprints of their host galaxies. Even in the outskirts of galaxies, they are found in zones thought to be inactive, showing that matter can condense into these mysterious objects wherever conditions are right. In starburst galaxies, galactic winds may reshape these dwarfs, redistributing material and affecting their mass and composition. This provides a natural laboratory for how substellar objects are shaped by extreme environments. Most supernovae leave behind neutron stars or black holes, but pure instability supernovae consume the entire star, leaving no remnant. They originate from extreme heat where high-energy gamma rays create electron-positron pairs, causing radiation pressure to drop and the core to collapse, triggering a runaway explosion. These are hundreds of times brighter than typical supernovae and were likely common among the first generation of stars composed almost entirely of hydrogen and helium. While rare today, certain modern candidates have stood out for their extraordinary brilliance. If such an event occurred nearby, its brightness would outshine the entire host galaxy. Unlike typical supernovae that fade over weeks, fast blue optical transients reach their peak in just a day or two and recede quickly. The first confirmed sample, known as the cow, was as bright as 100 supernovae but incredibly fast. Explanations range from failed supernovae to the tearing apart of stars by medium-mass black holes, or even entirely new physical processes. They are scattered randomly, appearing in both star-forming regions and gas-rich environments. Because they come and go so quickly, capturing them is immensely difficult. Imagine waking up to find that everything thoughts, experiences, memories is not real, but constructed by an external system. The brain in a vat concept makes philosophical doubt concrete, asking if we could be fed artificial signals without knowing. Our brains simply interpret electrical signals, taste, sunlight, and music are all encoded as neural pulses. If a system could replicate these perfectly, a brain in a vat would believe it is living a real life. If consciousness is an emergent pattern of information processing, advanced digital systems could host digital consciousness. This echoes the simulation hypothesis. If a civilization can create realistic simulations, it might create thousands of copies, making it statistically more likely that we live in a simulation rather than the original universe. To test this, some suggest looking for pixelated physical traces or computational flaws, but if the creator allows no errors, our search is futile. Even if we are a simulation, does meaning dissolve, or does it exist independently? Perhaps the question itself is the purpose of the experiment. Some planets are far more hostile than anything on Earth, with storms of molten metal and glass. On the gas giant WASP 76b, extreme proximity to its star causes tidal locking, where one side always faces the sun at temperatures over 2000 degrees Celsius. Iron vaporizes on the day side, is carried by powerful winds to the cooler night side, and condenses into liquid iron rain. On HD 189733b, silicate particles in the atmosphere create glass storms with winds exceeding several times the speed of sound, where liquid glass rain cuts through everything like blades. In hotter environments, atmospheres can be rich in metal vapors like titanium and aluminum, forming clouds of iron or sapphire. Carbon planets might even experience rains of graphite or tiny diamonds. These extreme weathers follow the same physics as Earth, just replacing water with metal and rock. Future spacecraft would need unprecedented heat shielding and armor, as any exposed instruments would be eroded by supersonic sand. If life could exist there, its biochemistry would be based on elements like silicon rather than carbon. One day, we may send probes to witness these deadly and magnificent storms, rewriting our definition of planets and the limits of life. Which cosmic nightmare do you find most terrifying, or have we missed something? That is all for today's sharing. I hope you have sweet dreams, and we will see you in the next episode.